Okay, welcome. Second day, still some days to go. So I just want to say all the course material, that means all exercise files you're going to be using, all the notes I'm making now in class, and an example is, it was converted to a PDF file that looks like that. Okay, and also the videos that I recorded one yesterday, and it looks fine. Okay, all of those are going to be on this website, which is my website, and I have a folder for this course. And you will find, I think now there are 4 folders or 3, one called exercise, one called notes, and one called videos. In the videos, you don't have the actual video, but there is a text file called link to video files, and I have uploaded to I think you were mentioning yesterday WeTransfer. Yeah, it's something similar, but that we use at our university. Okay, so you can just click on that link and download the video. The notes is not just that you won't take notes. I think it's very important that you yourself take your own notes, because my handwriting is far from perfect. I have to open. So I suggest really you to make the notes yourself. Okay? But if you need it for studying, for any purpose, you can use my notes. Okay. The link? Yeah, it's here.
Is that the one?
Yeah?
It's the same.
Yeah, the same. But now it's in machine letters, so it should be more easier to read. Okay, you don't have issues with my N or my S or the way I write. Okay, so let's we have all of these today. We're going to dedicate to try to put numbers in this flow equilibrium concept that we covered yesterday. Okay, you more or less understand how the curve should look like, why we do it, and what should we find when we make the intersection. But today is going to be what kind of equations we're going to use to calculate that intersection. Because we want at the end just to put numbers, not just to talk about it, where we have it, but just to be able to make a calculation. So if you remember, the first step, so we are going to have a well, we have certain reservoir pressure, we have PWF, which is flowing bottom hole pressure. Okay, that's what PWF stands for, flowing bottom hole pressure. And then we have there's something wrong with the pen. I think that the pen is not completely calibrated. Okay, so we have, at some point we have here wellhead pressure. Okay, that we assume is similar to separator pressure. So we have to make our equilibrium calculations. We have to go from the reservoir to that bottom hole, and that we do with one equation called IPR that we are going to discuss in detail maybe today, maybe tomorrow, if we have time. And we have to use that equation, which is called TPR, okay, tubing performance relationship. Okay? And we know how they look like. One looks like that, one looks like that, and then I have my intersection. But we have to know where these equations come from. So let's take a look first at the IPR. Okay, and for that, we're going to make just many of these models, IPR models, are derived in the same way. Okay, so so now we are going to enter a bit into IPR. Okay, not the full theory, but just some, just to explain something about when these equations are valid. So imagine we have a reservoir, which is like a cylinder. We have the well in the center. Okay, the radius is usually, it has a radius. Okay, it's not that it's just one point. It has a radius, but it's so small that we can just say, well, it's almost in the center. And then we have an outer bound called RE, okay, R external. Like the reservoir is the extension of the whole reservoir. So it could be that here there is a trap, there is some sort of a seal, there is a fault. It might be that you have, if you see from the top, you have well 1 and then you have well 2. And then one is draining that area and the other is draining that area. So this will be RE. Okay. But just for now, let's neglect that complexity. We just say is the extension of the reservoir is RE. Okay. So what I'm going to do next, I'm going to put an axis here that tells me the pressure. And then I'm going to put another line along the radius R to plot that pressure. Okay? So we're going to look at that pressure, what happens with that pressure along the radius. Okay, so here we have RE, and here we have RW, the radius of the well. So let's assume initially at time 0, everything is, I'm not producing anything. Okay, everything is at a constant pressure, that will be reservoir pressure. Everything is at constant pressure, is undisturbed, initial reservoir pressure, PRI. Now let's assume that I will be producing now my well any moment at time, so that's at time 0. At time 1, I'm going to open the choke of the well. I'm going to start producing the well. But the way I want to produce it here, I will have a constant bottom hole pressure. Don't worry about how I do that, but somehow I managed to keep the pressure at the bottom of the well constant. Somehow. What you will see, T1, exactly at the instant where I open the well, right? When I expose exactly the well bore at PWF, okay, you will have here PWF. But then all the rest, so I have a very strong jump like that, okay? All the rest of the formation will still be at PRI, okay, at the initial reservoir pressure. All the rest, only the small, like 1 centimeter or 1 millimeter into the close to the wellbore, that's going to be is going to feel that. But at that time, you're going to have a difference in pressure, right? That pressure is high and that pressure is low. That's what drives flow, right? Like in a pipe. So you will start to have displacement from fluids from the formation towards the wellbore. And that will cause the pressure to reduce, right? Because you're going to have less oil or less gas, whatever we are producing. So at another time, this area that is affected, so let's use another color, like that, is going to become bigger and bigger. Okay, so let's say that's for T2, and then we have another time. Okay, T3 and so forth. That period, when you see the boundary doesn't feel anything. Okay, the boundary is just there. It says, nobody's touching me. Okay, I don't feel anything. Whatever is happening here, the boundary doesn't feel it at all. Okay, that period we call this transient regime. Okay, and that means when pressure changes haven't reached RE. Okay, that's okay. When pressure changes haven't reached RE. But then I have at some point in time, after some time will pass, okay, you will have actually that something like that I have reached the outer bound. Okay, the pressure change, the migration of the fluid has reached the outer bound. Let's call this T4. Okay. At that point, the transient just stops. Okay, the stops being transient, and then comes two other regimes that are called so after T4. Okay, there are two options. Okay, one is the PSS, okay, or pseudo steady state. Okay, in which, well, the pressure in the bound is going to be reduced. Okay, because let's say it's isolated, doesn't have any inflow on this side, it's completely isolated. So I'm draining material and it's going to go down and down, and it will have more or less the same shape as T4. Okay, so let's see, I'm running out of colors, but it will have more or less the same shape, okay, but it will be reducing with time. And that's what I call the pseudo steady state. Even though it's not really steady state, right? That's why I call pseudo steady state. But it has the same shape, and I'm not taking into account all the changes have already propagated through the reservoir. Okay, and any change will propagate uniformly in every point, and it will start to reduce all of them at the same time, down and down and down. Okay, so that's the pseudo steady state. And or I have another option, which is simply just the steady state. Okay, and the steady state, when somehow, some reason, I keep the pressure at RE is kept constant. The pressure at that point is kept constant. That might be because I have water injection. I have another well here which is injecting and pushing and keeping the pressure high. Might be other mechanism, but I'm keeping that pressure at the bound constant. Okay, so clear the three regimes. Okay, so to know you see, I can find so for a radial well, we can have the following expression for determining what is the length of the transit, the duration of the transit. Okay, so it's 0.1 porosity, viscosity, compressibility, the area, divided by K, and you have a factor here called 3. Okay, and here the units are K in millidarcies. Porosity is a fraction. Viscosity, that will be in pascals per second. Compressibility, it's 1 over kilopascals. And A is a drainage area, which is in cubic square meters. Okay, So depending on everything, right? Depending on the length of your well, okay, on the area of your well, depending on the viscosity of the fluid, depending on the compressibility, if you have gas or if you have liquid. Remember that the compressibility is basically tells me how quick, if you had only the fluid, right? The compressibility tells me how quick pressure change travel in the fluid. If I hit the fluid someplace, then that's going to propagate, and how fast it goes, that is defined largely by the compressibility. But very important, which is a factor which is extremely dominant, is a permeability. Okay, so the lower the permeability, the higher that time is going to be. Okay, so if we say the lower K, the higher the time to pseudo steady state or steady state will be. Okay, I just yes, we are assuming here no, there is only one fluid. Okay, either gas or either oil, or yeah, you have only one fluid. So for example, if we try to put some numbers for porosity 0.3, viscosity, which this will be for a gas, okay? Okay? So if we have that system, the time, depending on the permeability, okay, it will be, it has the permeabilities, I have 10,000, this is in millidarcies, then I have 1,000, then I have 100, then I have 10, then I have 1, then I have 1, 0.1, 0.01. When I go in this direction, the time is going to increase, the time to steady state. Okay, so all of that is just to tell you that if you are depending on the conditions of your formation, on the properties of the fluids that you have, the extension of your well, and mainly due to the permeability, you have to be careful because you might be producing in transient, okay, or pseudo steady state, or steady state, depending on what condition you have. Okay, typically in many wells we are producing in so conventional reservoirs. The time, the transient, this time is very short. Okay, that means in the range of hours or in the range of a few days. Therefore, if I'm producing the rest of the year, I will be producing in pseudo steady state or in steady state. So I don't care really what happens in this transient. I don't care. It won't affect very much the production because most of my outtake of the materials from the formation will be happening in PSS. In PSS or SS, which is which we will see now why that's so important. But when you have a field where essentially the permeability is very low, again, we are talking here below 1, usually it's below 1 millidarcies, okay, then the transient becomes very important. The transient can last a few months to years to even the whole life of the field. For the whole field life, the well might be producing in transient. Okay, and then this approach that I use, I should use the transient IPR, not the pseudo steady state. Okay, so when when the well is in pseudo steady state, I can remove time out of the picture. Okay, the time is not, I can remove time and use reservoir pressure instead. Reservoir pressure will give me an indication of time. When it goes down, it just because more time has passed, right? And just use PR. And we will see tomorrow or maybe today, but most equations, so most IPR equations are derived from the diffusivity equation. Okay? If you remember those that are from reservoir engineering, what is it? For radial coordinate, that correct? I think. Okay, so you come with that equation, but if you have, you say, well, I assume that I'm in the pseudo steady state regime, I get rid of the time. Yeah, and I just have to make an integration of pressure along the radius. Yeah, and you say, well, that pressure will be changing, right? But that's how I introduce the change in time. With time, that pressure will be declining, 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 but that expression won't depend on time because I am in that regime. I'm in pseudo steady state. Okay, so just keep that in mind. These three regimes, and when each one applies, here you have a very simple expression to calculate it, and how IPR is derived. Okay, take that equation and start making assumptions. Yep, and we will see, we are going to do some of that tomorrow. But, so, for pseudo steady state, okay, okay, look like if you have just an undersaturated liquid, undersaturated oil, it just looks like a straight line. Okay, you have Q oil and PWF. That's how it looks like, and we're going to cover it. But basically, you can say that the rate of oil will be a constant times PR minus PWF. Okay. However, if you have gas or if you have saturated oil, okay, then the equation won't be a straight line anymore. Okay, Q oil or Q gas is going to be curved. And that's what we're going to use today in our flow equilibrium. Okay, that equation. So it's going to be curved. We will see now some of the reasons for that, but basically is because of the properties of the fluid that are changing with pressure. Okay, so the equation we are going to use is something that it was the first time it was derived was by the United States Bureau of Mines. Okay. Okay, and they were trying to find a way to say, well, how can I compare two wells? Okay. If I'm going to make an investment, I'm a banker, and then I say, well, where should I put my money? In this well or in that well? They have to have a way to compare both. Okay. For oil, it was very simple. You just say, well, I compare those that have J, right? I compare one J and the other J. So what do I do now with gas? So they made a lot of tests. Okay, and they end up with this equation that is called the back pressure equation. Okay, and it looks like that. QG at standard conditions will be a constant C that I call the back pressure coefficient, times PR squared minus PWF squared to the power of n. Okay, and this is the back pressure exponent. So we will see now, or maybe tomorrow, okay, this C contains information on the properties of the rock, the properties of the fluid, contains information about the geometry. So that contains a lot of things, but fluid properties, reservoir properties, contains information on the geometry, and also on the near wellbore effect. Okay, you see we have some effects that are close to the wellbore that are also included here. So what is n taking into account then? If we put almost everything in C. Is that the first time you see that equation? No? Okay. So n is usually a number between 0.5 and 1, right? When we are close to 0.1, close to 1, that means it's like a Darcy type flow. It's laminar flow. It's more Darcy. When we are closer to 0.5, that means it's a turbulent. Okay? And we can be all in between, 0.5 or 1. When I'm closer to 0.5, it's like this regime we have in pipes. Okay? That we have laminar flow and we have turbulent flow. So that's the equation we're going to use now for our equilibrium. C, and the reason why why they used that equation back, I think this was in 1930 something, okay, 1936, I think. And if, you know, to make a line, it was easy by that time, okay? They didn't have Excel by that time. So to make a straight line, it was easy to plot and easy to get the results. Now, when you start to make a curve, then the headache starts. Okay, how do I plot this curve? So, one of the reasons is, if you see that equation, if I apply log both sides, okay, then I'm going to end up with QG log of C times log of PR squared minus PWS squared. Okay? And it becomes a line. Okay, it becomes a straight line. So that means that if they come here, they come in a plot, and they plot the log using these tables, right? The log of Q and the log of the difference squared of pressure, they were going to get a straight line. Okay? And here they have the C, or log of C, and here the slope is essentially the n. Solve the problem. I don't have to use Excel, don't have to wait 70 years for Bill Gates to come and fix our life. We can do it in 1936. We now don't have that problem. We don't think about log. Actually, it gives us a bit of a nightmare to talk about logs. But you know, it's interesting to know where it came from. So that's the IPR that we are going to use. So I suggest we open the second exercise. Okay, it's called exercise 3, single dry gas well flow equilibrium. Okay, and we go to data. Okay, that's going to be also another homework, so I suggest you do the work on it. So for that well, we have, that's for the well, we are going to apply the equilibrium. Okay? So first, the first step is to calculate the pressure comparing all the way to the bottom of the well Okay, and for that we are going to use the IPR in this part here, and then we are going to talk about the tubing. And for that we have to introduce, the equation. What equation are we going to use? But if you see there in the input we have to calculate the IPR, right? That equation we have there. We have the back pressure coefficient, which is 104. We have N, which is 0.9, is very close to Darcy flow, and we have reservoir pressure. So let's try first to formulate these two rows. Okay? So now, before we start, I ask you something about that equation. How can we use that equation? Okay, this equation, how can we use it? Either we have pressure, right, and we calculate rate, or we have rate and we can calculate pressure. So I'm going just to do something here. If you use it like that, okay, you know that PWF has to be equal or lower than reservoir pressure, right? You know, because it cannot be higher. Otherwise, you will be injecting. So you know the physical range of that, and you know you won't have any problems. So you can try just different pressures below that. Now, if you use it the other way, which will be QG over C, okay? One problem you have there is that you have no idea how much the well is producing. What is the rate? What rate to use? So to have the whole range, it might happen that you assume some numbers. Okay, you have dreams. You think my well is an excellent producer. I'm going to make a lot of money with my well. Okay, and then you put a big number here, and that will give you just undefined. Okay, just an imaginary number. Doesn't exist. So I would suggest we use this form of the expression. Okay, we are going to give pressure, and then we compute the rate for that pressure.
Sorry, just a simple question. Did you change the basis and
On this block? So what? What did you say?
how did the coordinates change? What?
Well, we always have rate on the x and pressure on the y. Right? No. In all IPR equations, we always have the rate on the x and the pressure on the y. Okay. The only thing is that they found that if I plot it in log and I have to plot just this, so it took them a time to come to exactly the difference of pressure squared to get exactly that expression. Okay, so let's do that first part. Okay, so we know that pressure, we have to populate certain pressures. Okay, and that will be the equivalent if we come to our plot here, right? PWF, QG. So I want to divide in a few flowing bottom hole pressures from PR and down. Okay, and I want to compute for each one of them the rate. Okay, QG1, then QG2, and so forth. Okay, so we start by the first pressure that I should try is reservoir pressure, right? Even though it's zero, but it's part of the curve. So I come, I say that will be 304, and I block it. Okay, and then let's go maybe in steps of 50 bar. Okay, so let's try 250, 200, and so forth. Okay, so that will be my input. Okay, now the IPR, that equation, I told you, you won't have to do any programming in Excel. So we punch Alt F11 to see how the equation is called. You see here on the left we have, I think it's module 1. Okay, you see that there are a bunch of equations here, but let's look at the ones that have the name IPR. So IPR QG, that means that's the IPR equation that will give you the rate. Okay, that's the one we want to use, IPR QG. And I have another equation, IPR PWF, and that one gives you the pressure if you give the rate. That's the one that we might have an issue because of this minus here. So let's use the first equation, IPR QG. QG. Okay, then I have to give the C, which will be the same for all points. I block it. N also will be the same for all points. Reservoir pressure. Yeah, I can block it also. And flowing bottom hole pressure will be the number to the left without blocking, because when I drag it, I want it to apply for all others. And it makes sense, right? When I have pressure, flowing bottom hole pressure is equal to reservoir pressure, there is no rate. And when I'm going lower and lower and lower, I'm getting a higher rate. Okay, a higher and higher and higher rate.
So can we go back to the function?
Yep. Okay, back pressure coefficient, the back pressure exponent, reservoir pressure, I can take it either from here or from there, and the PWF will be changing. Okay, so that's why if I drag it down, I want it to use the number to the left. Okay, and here we see how it looks like, and exactly looks like what we expected, a curve. Okay. The point here, when we have at 0, which is basically vacuum, okay, I'm putting the bottom hole at vacuum, something that we will see later I cannot do very well. This point is called absolute open flow, okay, AOF. It's when I put, somehow, I managed to put my flowing bottom hole pressure all the way down to vacuum. It's called AOF, absolute open flow.
The first part of the PWF is the one from the reservoir pressure.
Yep. We know that our PWF will be between reservoir pressure and below. So that's what I tried, and the others are just random numbers in steps of 50. You can use any step you want. I just want to use 50, not to have too many numbers. Okay, this number here will be AOF, so that's the absolute open flow. Okay, when somehow I'm producing and I put the flowing bottom hole pressure to vacuum. Okay?
Sorry. I didn't understand your explanation. What is the meaning of this absolute open flow?
It's just a number. Just if the rate that the reservoir will produce, if I put somehow the bottom of the well in vacuum. So it's the maximum rate that I can get physically possible from the well. Okay, that's just a number. That's just that's just an explanation. Okay, clear so far? Clear so far? Yes? Okay. So now let's go to the second part of my puzzle, okay, which is to calculate the other curve that we want to intersect, this TPR. Okay, that is the tubing equation. So for that, we have to do, it has to be, we have to go through a bit of a boring process. Okay, so I hope you will stay awake and also help me to see if I have any errors. Okay, but we have to start with equations for pressure drop in the tubing. Okay, or the tubing equation. Okay, the tubing is essentially a pipe. Okay, it's a conduit. So I have to calculate pressure drop in a pipe. Okay, pressure drop in a pipe. And the problem is that it's essentially is compressible fluid. Okay, it's a gas. So that's one of the challenges we have to see how we tackle. Did you cover this some other course? Pressure drop with gas? Some fluid mechanics course you have? Yeah? Okay. So what is the expression for pressure drop in a pipe? This guy Bernoulli equation, right? Okay, so that we define dP over dL along the pipe will be equal to, you have three components, right? Three contributions. One of them is first the hydrostatic difference, right? Which is density, gravity, and yes. So here we have the angle, right? The inclination angle. But I'm going to define my angle. So if I have my pipe like that, okay, I'm going to define my angle here, this alpha, okay, from the vertical, like grillers. I'm not going to define it from the horizontal. That's when we use it for transport. But for the tubing, I use it from the vertical. So here I have the cosine of alpha. Yes? What else? So that was hydrostatic. Now I need frictional losses, right? So how do I write that? I have a friction factor times the density divided by 2, diameter, velocity squared. Right? And just be careful, what friction factor I'm using here? Remember, there are two types. Okay? We have Moody and we have Fanning. Okay, we have two friction factors. So here I'm using the Moody friction factor. Okay? So what is the complexity of this equation? If it was a liquid, right, or an incompressible fluid, I can just substitute that will be a constant, the density, right? And here I have friction factor I calculate with that graph. Now with gas, the density will be changing with pressure, so it's a function of pressure. So that's the main challenge. So that means that the equation has to be integrated. Okay, I have to integrate, and I have to take into account the change in density. So how do I express that? The change of density as a function of pressure. If you remember from last class, just the real gas equation, right? We have one equation that says P over density is set RT, right? As we were discussing last class. So we can say that density is essentially set RT divided by P. Yes. So we come and we substitute that in this equation. Hmm? Yes? Yeah, it's actually the opposite, right? But that someone is awake. So in this equation, this differential equation is like P is Y, right? And X is L, okay? So you see that Y appears here and here. Now you have gravitational acceleration, the cosine of alpha, plus F times, and here I have to use two diameter, the density, which is pressure, divided by ZRT, and the velocity. But the velocity is also going to change depending on the pressure, depending on the density. So how do we say yesterday that will be a good way to put it? The velocity is equal to the local rate divided by the area, right? And this, at the same time, this is mass flow divided by density divided by the area, right? So let's use that expression here, velocity squared. It's going to be a bit messy. So we have F. Actually, one of the densities is going to be, so you have mass flow squared, and the area is pi diameter to the 4, and then you have 16 here. Okay, is that correct? And here I have a 2, right? That correct? I just took away one density from here. Then I have just one density, mass flow squared, and the area. And yeah, I'm missing here. Yeah, density. This was density. Okay, that I just took it away. So at the end, I end up with. So let's try to put it again. dP dL. Pressure G. And here I have my density, which is pressure ZRT. Okay? So now to make my life simple, I think so, right? You're the ones checking what I'm doing. Okay, so you're the ones that have to be awake. Okay, so let me check with my, do you call it also chuleta? Here? Chuleta? Do you call also when someone is in an exam and you have some paper that you use for support? How do you call it here? Cábula. We call it in Spanish, it's called chuleta. Like, you know, this thing you eat from the pork. Yeah. Okay, so we now, to make my life easy, I will say, well, this is y, right? This is in principle is a constant. So I'm going to call these two constants. CA will be G cosine of alpha divided by ZRT, and CB will be F times 8 sorry, the P shouldn't be here. ZRT m squared okay, and now I end up with the following differential equation: CA times P plus CB divided by P. Okay, and remember, how did I solve these type of equations? If you remember all time back, like yeah, maybe 10 years ago, how do I solve these type of equations? I have to separate, right? To send everything that depends on pressure on one side and everything that depends on length on one side. So I do variable separation, dP divided by CAP plus CB over P, and this will be equal to minus DL. Yes, I separate everything that has to do with pressure, I put it to the left. Everything that has to do with length, I put it to the right. And in this case, I don't have anything, almost anything to do with length. Yes? Okay. Now the next step, the snakes. Okay? I integrate from, where I'm going to integrate from? From, no, this is in the tubing, right? So I'm integrating from the inlet to the tubing. How do we call that point? Flowing bottom hole pressure, right? PWF all the way to PWH, to wellhead. And I integrate the length also the same way, 0 to the top. Let's call this L should be small l, and this is big L. Flowing bottom hole pressure. Okay, the pressure at the inlet of the tubing. Okay, and I end up with, so this will be simply L, okay, just the length of the tubing, not the difference in height, but the total length of the tubing. And now I have this integral. And here I'm going to have to use the help of my friends which are good in mathematics. How do I solve this integral? Do you have this professor called Kalashnikov? Did he teach you? Yeah? Math? So should we bring him here to kind of see if you remember or not? Better not? So how do we solve this equation? Okay, first I'm going to make my life a bit easier, I'm going to multiply above and below by P. Okay, so I'm going to obtain P dP, and here you have Ca P squared plus Cb. Okay, and if you see here, what I have below, the derivative of that is almost the same as what I have above. Okay, so I can use a method called, how is the method? Okay, essentially I can say, well, U now will be Ca P squared plus Cb, right? And then du will be Ca2 dP, P dP. Okay? And then I have to just substitute on my equation. Okay, and when I substitute, I get, I have to use a trick, right? Because I don't have this factor. So I have to divide by 1 over CAD, and I get du over u from, and here I have to integrate from u1 to u2. Okay, from two limits, from the bottom of the tubing up, that will be minus L. Yes, that integral we know. How do we solve that integral? Just ln, right? Natural logarithm. So this will be natural logarithm of u evaluated between u1 and u2, okay, minus L. I'm going to actually put the minus here, 1 over Ca times 2. Now, there is something that you didn't notice it, and I didn't say anything. What are we assuming here in all of this development when we have made that integral? We made one assumption, right? The assumption was that these factors Ca and Cb don't change with pressure. And is that correct? If we see, what were these factors CA and CB? Okay, that's fine, right? G, alpha, but now R is also a constant for the gas, but you have Z and T. And these are going to be changing with pressure and temperature. So, to make my life easy, I will say, well, yes, they are going to change, but I'm going to use for the integral these numbers using an average value. Z average and T average and CB will be calculated using T average, and it's equivalent to say, yes, it's going to change, but really what makes or drive the change in density is mostly pressure, is a change in pressure. We know all the others are going to change. So we are going to use an average for those properties, and then we are going to check if we are okay or not. But just that we can make the integration in pressure. Okay, so here T average is defined as TWF plus T wellhead divided by 2, and Z average is Z bottom hole, Z at the wellhead divided by 2. I'm not sure why my G look like a... And that's one assumption we have to be very careful. We are assuming that the tubing has an average to calculate CA, these constants CA and CB, as an average temperature and an average deviation factor. Okay, so with this minus, I can just invert the logarithm, right? Okay, so I end up with what? Okay, I'm going to pass that to this side, L times CA times 2, and I'm going to change a ln of U2 divided by U1. Sorry, U1 divided by U2. Yes? Okay. So now the next step, I'm going to put the exponential. Okay, I'm going to apply exponential both sides. E to U1 over U2 equal to E over LCA. And that factor I'm going to call S. Okay, so S will be L times CA times 2. And what was the definition of CA? CA was G cosine of alpha to L divided by ZRT. Okay? Yes? So if you see here, we have the length of the tubing multiplied by the cosine of alpha. What does it mean? What is that telling me? It's just the difference in height, right? Between the inlet and the outlet of the tubing. So that, if I have no flow, that will tell me that the difference in pressure will be just the exponential of some height, okay, some difference in height. Like if we apply for, we are going to do it just now, okay? So I'm just defining, I'm saying S is a factor, is the elevation factor we are going to use in our equation. And you see it has these two, L and the cosine of the angle, which is effectively the difference in elevation. Okay, so let's see what was U1 and U2. So U1 was was at the inlet of the tubing, right? C CA PWF squared plus CB, right? And U2 was CAPWH plus CB, right? So I have, sorry, that's wrong, okay? Because that had a land, so this should be, okay, this should be like that. So here I have CAPWF plus CB divided by CA. Is it PWF? Yeah, PWH plus CB equal to ELCA2. Yes? Let's see if I didn't make any mistake. Okay, actually the minus I kept, yeah, I think that's fine. Okay, then I can rearrange that equation. Okay, and then I can further rearrange. I can take out, let's see, can divide by CA. Okay, and then I can have PWF squared will be equal to E to the S PWH plus CB over CA times E to the S minus 1. Okay? I end up with that equation. I hope I didn't make any mistake, which might be. So what is CB divided by CA? CB divided by CA was, you have to find the definition of CA and CB. It was 8 and CA is ZRT divided by G cosine of alpha. Okay, and here, so I have already almost, I have everything I need. Okay, I have pressure at the bottom, I have pressure at the bottom, I have a factor S that I can calculate, right? So now I need, in this equation, I need rate. Okay, and rate comes when I make the division between these two. You see here appears the mass flow. And the mass flow we learned last class that it can be associated with the standard condition rate, right? So we have almost everything that we need in that equation. The only thing we have to substitute that in here, okay? And then we have to change this match flow and have standard condition rate instead. Okay, so how do we do that? The last step, we just need one more step and then we can do the exercise. Let's see if I didn't make any mistake. Okay, so I say the mass flow, it was equal to Q standard conditions times the density as standard conditions, right? And the density of standard conditions I can express as P standard conditions divided by T standard conditions times R. Yes? Okay, so then I substitute that in this expression. I end up, so that's the last expression I'm going to write. QSC, that will be squared. Okay, then I have to be careful. 8F. Okay, and this R actually goes out with that R. Okay, and I have here e to the s minus 1. Okay, and that's, I present to you, that's the tubing equation for gas. Here we have everything we need, right? We have pressure, and then we have the rate. And we have a bunch of constants that are going to make your life easy, and you don't have to worry about that. It's already pre-programmed in Excel for you. But I think it's important just to see everything that it has inside. Okay, how do we derive, how do we come to that equation? And that equation, so the last way how we write it, it's not here actually.
Can I see what S is up with?
Yeah, S is this guy. Okay. Okay, and so all of that we call let's see how the okay, this is everything that I call CT1 over CT squared. Okay, and I call this one, I call the elevation coefficient, and this I call the tubing coefficient. Okay, the CT. So at the end, the expression ends up being PWF squared equal to PWH squared e to the s plus Q standard conditions divided by CT squared. Okay, that is actually the same expression we have, should be the same expression we have here. Okay, P inlet equal to P outlet multiplied by e to the s plus the rate divided by CT. Okay, so that I present to you, that's the tubing um, the tubing equation that we are going to use now in this exercise. Okay. So what have we done first? Let's try to summarize all of this math that is making our brain, hurt a bit. So what have we done so far? We came from the Bernoulli equation, right, for pipe, and also one important thing we have neglected here, this acceleration change, right? The change in velocity in one section of the pipe is just we have neglected, okay, which is not 100% correct, but it's an approximation. The next thing we said, well, the equation has density, and we know density changes with pressure. So we have to put that in the equation somehow to eliminate the number of unknowns. So for that, I used the real equation of state, right? We're using set. I substitute that, and then I say, well, now I put the velocity, the next step, in terms of the mass flow, because I want to have a constant which tells me how much my system is producing, the mass flow. And then I end up with this equation. The next step, I create constants just to make my life easy. Okay? And then I just integrate, separate sides, everything that depends on pressure on one side, everything that is constant on another side, and then I integrate. And the main assumption there is that, yes, pressure is going to be changing from P bottom hole to P wellhead. But these properties, the Z and the T, they are also going to be changing. But we are going to say that we are going to use an average number that, it will capture more or less the variation of Z and T. And after I do that, I integrate, I do some more magic, and I substitute the mass flow by the rate at standard conditions, and I end up with this equation, which is a dry gas tubing equation. Dry gas tubing equation. Okay, so if you go to your Excel sheet, if you go to tubing constants on this sheet, you will see you have the calculation of S and the calculation of CT. And you can put any value you want and calculate for any tubing you have. Okay, so for example, the height difference, that will be, not the length, but the height difference, line length. In this case, when both are the same, we just have a vertical well. Okay, the ID, the internal diameter of that tubing, gas gravity. Well, we need the gas gravity, if you remember. Here we're using PV equal to RT, and this R is the universal gas constant divided by the molecular weight. Okay, and if you remember, the molecular weight of the gas is the specific gravity of the gas multiplied times the molecular weight of air. Okay, so that's why we need the specific gravity of the gas. Okay, because we want to calculate depending on what fluid do we have. Inlet and outlet temperature. If I measure it, right, I know the temperature in the reservoir, I know the temperature at the wellhead, so I can use the average temperature. Inlet pressure, I have no idea, right? But I assume, I say, well, the pressure, the highest pressure it can have is reservoir pressure. And the lowest pressure at the outlet of the tubing is separator pressure. So I use those two as a starting point. Okay, then I calculate average deviation factor, average temperature. I calculate, friction factor. That's something very important. How do I calculate the friction factor? Yes, laminar, turbulent, and then I go, so I calculate my Reynolds number. Okay, and then I go to this chart. So the friction factor versus Reynolds, okay, is something like that, then going up. right? Okay, the Moody chart to find F, and the Reynolds is not sure why I use this. Reynolds, the density, the diameter, the velocity divided by the viscosity. Yes. So here for gas, there is something very interesting. Okay, and it's something that is very nice that it happens. For gas, actually, that number is very, very low. The viscosity of the gas is just very, very low. It's usually a number 1 to the minus 5 pascals per second. Okay, it's a very low number. And that makes the density is also usually low, right, compared to a liquid. So that makes that number is usually very high. And if it's very high, usually gas is just on that side. So that's, how do we call this regime? Fully turbulent, right? Okay. And on that regime, really, the friction factor is not a function of Reynolds anymore. Okay. In this regime, fully turbulent, the friction factor doesn't depend on the Reynolds anymore. If you see, there is relatively flat, constant with the Reynolds. It's a function of what? If you remember, these lines had a few E1, E2, E3, E4, right? And that was the roughness, yes, for the pipe. So that was that E, if you look at the pipe and you see the imperfections it has on the wall, okay, so you take a closer look at those imperfections, okay, and you take the distance, let's call it E, epsilon will be E divided by the diameter, okay, the roughness of the pipe, but in that case, just a dimension. So at the end, for gas, we can reach to the conclusion that for gas, the friction factor is just a function of the roughness, which is fine, but still we need to have an expression for that. But then so that was in the 70s, I think. Okay, a guy called Smith, okay, in the 1950s, Smith found, this was in 1950, he said that the roughness is actually a function of the diameter. He did many tubings from many different mills, from many different workshops that they were making tubing, and he finally said, well, the roughness really depends on the size. Okay, if I have a small tubing, I have certain roughness, and if I have a big tubing, I have a certain roughness. So he said, he proposed actually for gas, we can use the friction factor will be just a function of diameter, and it will be 0.0077 divided by the diameter to the 0.224. Finish. I don't have to calculate Reynolds, I don't have to calculate density, I forget about all of that issue, right? I just use a factor that depends on the diameter. And that's very nice with gas, okay? If we had liquid, we have to come and calculate Reynolds, do the whole process. Okay, so I think that's the expression we have here in the exercise. Its friction factor is here, FF. Okay, and finally, with all of that information, you can calculate S and you can calculate the tubing constant. If you go and punch Alt F11, we're going to take a break soon. You see, S is exactly the same formula I showed you before. The height difference, the average set, average T. This friction factor is just the equation by Smith in 1950. And then the CT is the other, a bit more complex expression with, you have all of those concepts. So after we have CT everything, right, we can now calculate this part, the tubing equation, okay, which is only that equation here, okay, this equation here. Clear? More or less? Now we are going to use it, okay, but I just wanted to show you where it comes from. We have to integrate, okay, no, we cannot use one density and then use it for the whole tubing. We have to do it step by step. When we come to multi-phase, we won't be able to integrate because all the expressions will be, in this case, I could use, the expression of the real gas law. Okay, I could use that. And by making some assumptions, I can say, well, I can use average properties. In multi-phase, things change so much that I cannot use this approach. I have to do it segment by segment by segment. Okay, and so I have to make a numerical integration. In this case, I can make an analytical integration, and I found a formula which is very convenient, okay, and very powerful. By using average properties, average S and average CT, I can reproduce the whole pressure drop in the tubing. Okay, should we take a break before we make the exercise? Yes? Okay. So let's say... Okay, gas is, is a bit easier if we... First, gas is very relevant for you. You have a lot of gas reserves, offshore and onshore. So I think it's important that you get familiar with gas, with the tools we have to analyze gas. And liquid is a bit simpler when we have just undersaturated oil. But you have this complexity on the friction factor. Okay, so that's why I decided to go to gas first. Okay, so we have our exercise. We have calculated already this curve, okay, the IPR. And now we want to calculate the TPR, which we're going to make with this equation, the dry gas tubing equation that I explained just now in class. Okay, this equation here. And that equation has, I promise, is already pre-programmed for you. If you go to module 1, if you punch Alt F11, you see 3 equations that are called tubing. Okay? Tubing Q, that tubing you give the 2 pressures and it will give you the rate, right? Then tubing P1, that equation, you give the pressure, P2 is the pressure at the discharge of the tubing, that means P wellhead, okay? And Q, and you obtain P at the inlet of the tubing, which is the bottom hole. Or you can calculate P2, the pressure at the outlet of the tubing, by using the pressure at the inlet of the tubing and the rate. Okay, so now I ask you to see if you're not sleeping. Tubing P1, is it counter current or co-current calculation? P1. I have P2 and I want to calculate P1. Counter current, right? So is the available pressure, the required pressure at the tubing inlet. P2 is co-current, right? I'm going from the bottom hole all the way to the wellhead. And that's the available pressure at the wellhead. So which one of these 2 equations should I use for my case now? Remember, it helps to make a drawing, right? To make a sketch. The system, we haven't presented the system yet. It's a well called EVA, number 3. We have a reservoir, PR, PWF, P wellhead, and we are saying it's very close to a separator, P separator, so P wellhead is almost similar to P separator. So far we said the equilibrium point will be at the bottom of the well. Okay, that we define arbitrarily. We define bottom of the well. So then we came from reservoir pressure here, co-current, with the IPR equation, right? And we just found something like that. Okay, PWF. Now, what is the next step that we discussed yesterday? We have to look for the other boundary, right, where we have constant pressure. Where is that? Separator. And we have to go counter current all the way down here, right, to compute that pressure. So for that, I'm going to use that expression, PF equal to PWH plus QG over CT. And I'm going to use it exactly like that. Okay, I have wellhead pressure. The separator is making sure that I have always that pressure. The rate, that's the numbers that I'm going to change. And the CT, that's something that I estimate, right? And the S also. So then I can compute the pressure. Is that pressure available or required? Required, right? So is the pressure required at the inlet of the tubing to be able to flow that rate against this pressure, this wellhead pressure. Okay, so let's try to do that, okay? So what equation do I use here? TPR. Let's look for it, okay? So let's say I know it has to be tubing, user defined. Tubing P1. Okay, I want the pressure at the inlet of the tubing. CT, which is this number here, and I have to block it with a 4. S, the elevation coefficient, and I have to block it. P2, the pressure at the wellhead, which is similar to the pressure at the separator. And the rate, what rate do I use? Well, we don't know yet, right? We don't know the rate, but we know that if there is any intersection, either here or here or here, the intersection has to be between in this rate range, right? It has to be if there is an intersection. So that means I can use the same range that I use for IPR. So let's do it like that. Okay, I don't want to try any numbers here. I know the intersection is not there. Okay, and I don't want to try it. So I will try numbers in this rate, in this range of rates. So for that I say the rate will be simply this rate. Okay, that I just calculate. The same rate that I use for the IPR. Okay, let's see now how the graph looks like. Did you get something like that?
Yes.
Yes? Okay, good. So we know the intersection is here, right? That's my equilibrium point. If I put these two together, that reservoir and that tubing, they are going to be producing on that rate. Okay? But how do I find now exactly that rate in Excel? Or in any program? How do I find that rate? Yeah, so so how to find the equilibrium rate, okay? Okay, so basically I have to find, and that's what many software that you use in production, that's what they do, right? They use that equation, and then they use this equation and they solve those two equations simultaneously. How many unknowns I have in the first equation? So I have, this is an unknown, right? And this is an unknown, but all the rest are knowns, right? So I have two unknowns and one equation. And here I have another unknown, which was the same as I had before, and this unknown that is the same that I had before, and all the rest I know, right? So I have the same unknowns, but I have one additional equation. So I have 2 and I have 2. That means I can solve. Okay, I can solve the intersection. So a way that we are going to do that in Excel to avoid, going when the equations become, that's fine, we can make it analytically. Some of you that are very good in math, you can go and say, you can exactly clear analytically the solution, right? When we go to multi-phase, we go to even single phase, the expression becomes much more complex, okay? That means that I cannot just take the two equations and try to find the solution. I cannot. I have to find another method. So one method that we use for that is root finding. Okay, that sounds familiar? Some course in numerical methods you have some time ago. You have some methods, right, that they allow you to find an x such that makes this function equal to 0, right? You know these methods? Yeah? Like if you have a function, okay, that the function behaves something like that, okay, you calculate, is for example Newton-Raphson, okay, you calculate the derivative, okay, then you shoot with that derivative, then you find that point, then you shoot with that derivative, then you find that point, you shoot with that derivative, you find that point, and so forth, right? That's Newton-Raphson. Or you had also another method called bisection. Yes? Did you cover that some time ago? Okay, fx, that you take 2 points, one called A and one called B, where there is a change of sign of the function, and then you make the average of both, okay? Let's say that the average is here, A plus B divided by 2. You say there is a change of sign, this will be now my new A and B. I make another average, then this will be my A and B, and I go closer and closer and closer. Yeah, bisection or Newton-Raphson. So we are going to do the same, but you don't have to worry remembering how it is done. Okay, we're going to leave that to the machine. So the way we're going to say we have two functions. In this case, we have two, right? We have IPR. So that's going to give me a PWF, right? So that will be my function 1. Then I have another equation, TPR. That will be my function 2. So, and I want exactly to make function 1 equal to function 2. PWF from the IPR should be the same as the PWF from the TPR. But that's not how these root finding methods work, okay? They cannot make two things equal. They have to find when a function becomes 0. So how do I do that in this case? I just create a third function, right? This trick that you say, well, I create f3, that is f1 minus f2, and then I want to find the x such as f3 will be equal to 0. And in that way, f1 will be equal to f2. Yes? So I have to put the difference between them. So that's exactly what we're going to do in this exercise. We're going to have, you see here actually there is another column, okay, where I have the available, that's the one that comes from the IPR and they require, the one that comes from the TPR and the difference, and that is the function I want to drive to 0. So let's, on that column, just say calculate that number, PWF minus this PWF. They have to be for the same rate, okay? So be careful. Okay, so we obtain that more or less. Okay, I hope you're getting the same number. And you see here our function, this will be our function F3. Okay, and here you see positive, 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 and negative. Okay, so that's your function F3, and you see here you have a change of sign. That means that your root is someplace, so your PWF solution star is someplace between 100 and 50 bar. Okay, it's someplace in that range. Okay, and now we have to use something, some solving method, to usually use it in this column. Okay, we want to change some variable, okay, to drive that to 0. So what variable are we going to change here? What is the x? So what x did we use in our Excel sheet? This is calculated, right? So this should be in blue. This is something we calculate based on that. And this is also something I calculate based on that, okay, on these two, on this one, sorry. So what I'm going to use as the independent variable is actually PWF. Okay, I will change PWF. So let's say here 90, for example. You see I'm getting close to 0. Then I try 87. Okay, then I pass below 0. So you know the solution has to be between 90 and 87. Okay, by changing that number. To find exactly the solution, I use something called solver. Those of you, it should be here on data, solver, to the right. If you don't have it, you have to go to File, Options. You have to go to Add-ins. Then you have to click Go at the bottom. Okay, and you have to click in, it's called solver. I'm not sure in Portuguese is the same, yeah, solver. Okay, so you have to make sure you click it. After you click it, it should appear on the data tab. Have any of you used the solver before? No? You don't get it? Okay. Okay. Then we open the solver. Okay. And the solver says first, tell me what do you want. Okay. So you say first, I want this cell. Okay, so we are going to use this cell. You could use any of the others, but I want to use a cell which, you know, I don't want the point to jump out of the curve. Okay, I want to continue the same trend as the rest of the curve. So that value, that cell, I want to drive to 0. You can do other things. Okay, you can maximize, minimize, drive to 0 by changing this pressure, that number. Okay, has to be on the same row. Verify that you have 21 here and you have 21 here. And if you want to help the solver, in this case it's not very critical, okay, because you know what is the range. But if you want to help, you want to say also that that pressure has to be less than reservoir pressure. Just to give it some help, such it won't start to try very big numbers. Okay, you know already where your solution should be. Yes?
How we get the last step?
Just click Add here.
Just to add.
Just click Add, and then you get this window. Okay, and in that window you select, you say that the cell you're going to change, the variable x, has to be less or equal than reservoir pressure. Okay, and then I click solve, and it found the solution. My bottom hole pressure, unique bottom hole pressure, if I put these two things together, they're going to be operating at 88.3 bar, flowing bottom hole pressure. The rate, 2.83 million standard cubic meter per day. Just wait, let me copy this here. When we were calculating the constant, right? We didn't know what rate what pressure the tubing will be operating with. Okay, so we said, if you remember, the pressure we used for the inlet, okay, was reservoir pressure. But now we know it's not reservoir pressure. Now we know it's 83, 82 point something, 88. Okay, so let's see how that affects the CT. Okay, so instead of being 304, now it's 88.3. Okay, 435. So that's the real constant that I should have used. Okay, 435. So I can go back, just copy that number, or I just write it down here, and I put 435. Okay, and you see, does it change now the equilibrium very much? Hmm? To calculate, if you remember what we have done at the beginning of the class, okay, we should. We are using some average properties, okay, average temperature and average deviation factor. That one is calculated with an average pressure, but we don't know yet, right? That's something we have to calculate. So we assume. Okay, we assume here in the tubing constants, we have assumed that the inlet pressure, we have no idea what was going to be the inlet pressure to the tubing. So I assume reservoir pressure. I assume. Now, from the equilibrium, I found that actually my pressure is not close to reservoir pressure, but it's actually closer to separator pressure. Okay, so it should be 88. So to fix that, what I have done is that I came back on the tubing constant and I changed. Instead of using 304, before I had it like that, now I'm going to use 88.2.3, okay? And you see how it changed. The S changed and the CT changed. So I have to change now the numbers. 302 is S, 302, and CT is 435. Okay, you see now that the solution I had before, 88.3, it doesn't give me now anymore 0. Okay, it gives me minus 0.5. So I have to repeat this over again to find the intersection. Okay, 88.8 instead of 88.3. Then we have a small difference. Okay, a very small difference. So really, it doesn't matter. Usually, in many cases, it doesn't matter the pressures that I assume for the tube, right? It doesn't matter much. Okay, it's going to affect somehow my equilibrium, but it's not going to affect it very much. Okay. Okay, now we can do many things with this curve, okay, with this system, with this well. For example, what will happen if I increase the tubing size? Okay, if I use a larger tubing with a bigger diameter. Which curve is that going to affect? Is the blue curve or the red curve? Yep.
You can go back on that value that you changed.
Here?
Yeah, which value?
I changed the S and the CT. Okay? According to the numbers that are here. CT 435 and the S 0.302. No, I changed it here. I read the numbers from here and I write them here. Okay? This one. B5. This one. This one. No, that we are going to do later. That's a flow line. Okay? That's another example. Okay. So what's the effect of the tubing size? What's going to happen if I use a larger tubing? What do you think? Let's say, think first like logically, okay, just by intuition. If I use a bigger tubing, yes, but I will get a higher rate, right? Because it will be not the restriction, the velocity will be lower, and then I have a better flow. So the intersection should move where? To the right or to the left? To the right, right? To get a larger flow. It should be here. So if I use a larger tubing, it doesn't affect the static height. It will be the same length, the same difference in height. But now my curve will do something like this. Okay? So this is phi1 bigger than phi. But you see the increasing rate is very, very, very small. That means that basically my system is not limited by the tubing size. Okay, I'm using a very large tubing size. If I use a smaller diameter, the rate will decrease. Okay, that means the intersection will be someplace here to the left side. So that is a tubing size 2, which is less than phi. How does that reflect on the CT? If you remember the equation of the CT, we have to go way back. Yeah, CT. You see, CT is essentially proportional to phi to the 5. So every time I increase CT, every time I increase the diameter, CT is going to increase. Okay, every time I decrease it, so very big tubing that has no problems to flow has a big CT. Small tubing where you have a lot of restriction to flow usually has a small CT. Okay, and you can just try. Okay, you can just try in your example. If you now use, for example, let's try with this was a 5-inch tubing, I think. Let's try with a 2 3/8. Okay, 2 3/8 is 2375. And it has to be in meters, 25.4 divided by 1,000. Okay, From 1.5, now it's 0.06, and now I have the same elevation. The elevation coefficient is not affected by the diameter, but the CT is, and you see it reduced dramatically for 4.35 to the 4 to 3.57 to the 3. So I tried now that number, okay, and the intersection, you see now how it affected very much the tubing equation. Now the intersection is not anymore a 2.8, but now the intersection is here. Okay, reduce dramatically the rate of my So let's just take it back to the number it had, and so let's make here a small comment. So what affects the tubing size? Okay, how do I decide, or how do I design a tubing size? First, you want to maximize production, right? So if I tell you, if I'm, let's say, let's say I'm a manager, okay, and I say, now, we are operating with the red curve. So I have an idea. I say, if we put a bigger tubing, that will increase dramatically the production, and we are going to make big bucks. You, like engineers, do you agree with my phrase or not? With my idea or not? If I say, we have now this tubing, right? The red one.
Yeah.
And I say, I have the great idea, I'm very brilliant. Let's say we are going to increase now the tubing size, make a complete operation to make a workover, to take out the tubing and put a new one. I'm going to produce much more. What do you think about that? Not, right? Because really, if I increase it, the increase will be very small, will be very minimal. And that you can do from this plot, okay? While if I had the other intersection here, okay, like what we were looking before, and you say I want to increase the tubing size, that can give you much more, okay? That can be a very good increase in production. So I have to use a tubing size that doesn't restrict production. Okay. What other factors do I use for tubing size? Of course, it has to fit on the production casing, right? I cannot use, so it has to fit production casing. Yes?
How do I know that this is the right size? How do I make sure this is the right size?
Yeah, that's exactly the list, okay? One of them, you want to maximize production such that the tubing won't be a constraint. Okay, like if the rate you want to produce is someplace here, you want to get a high production from the well, but you are here, that indicates you are restricted by the tubing. Okay, it's tubing restricted. If you are here in that range, that means you're not tubing restricted. Your tubing is too large. So you have to be someplace in between. Whatever, big tubing costs money. And to replace the tubing costs money. So you have to use a number in between, that not too large and not too small. Okay? But there are other things. One of them is that it has to fit your production casing, okay, which is normally 9 and 5/8. Okay, so that's almost any tubing can fit. What is the other thing that we have to consider? Okay, one thing is erosion. Okay, the velocities in the tubing has to be less than the erosional velocity, and that we are going to discuss a bit later. Well, you already know how to calculate velocity, right, along the tubing. That's the exercise we have done yesterday, but that's according to API 14E. There is a way how we have to, so the velocity has to be less, the gas velocity has to be less than the erosional velocity. Another thing we have to take into account is liquid loading. Okay? Liquid loading. Very seldom we have just pure gas flowing through the tubing. In most cases, we have some liquid coming with that gas. And that liquid is usually in the form of droplets, okay, that they are dragged up by the velocity of the gas. If that velocity, so you have two forces acting on the droplet. One of them, which is mass times the gravity, and then going up a drag force by the fluid. So if those two forces are equal or less, then the droplet will tend to deposit on the well. And then you have an accumulation of droplets with time in the well. And that's bad because you have, if you look at your tubing, okay, you look at your reservoir, you're going to have an accumulation of liquid, and all of that liquid creates a hydrostatic height, okay, that is creating some back pressure against the. So the velocity of the gas has to be greater than the unloading velocity, okay, and that is just, you will see now, that's a criteria called a guy called Turner. That's what we normally use in the field. What else? We have to, there is one thing that we have to, depends on the size of the tubing hanger. Okay, if you remember, we had our tubing, right? And we have here at the top, with the casing, something that is called the tubing hanger. Okay, and it's something that just keeps and holds all the weight of the tubing on and transfer it to the production casing, then to the intermediate casing, then to the surface casing, and then to the conductor. Okay, it's transferring all the loads of that tubing to the ground through the conductor. Okay, and that usually looks like like a disc. Okay, I can show you some pictures before, but it's a disc where you have a main hole for the tubing. Okay, this disc is supported somehow back here by some like a no-go shoulder. Okay, actually it looks something like that, and then you have your disc, something like that, and then you have a hole to connect the tubing here. Okay, but the problem is that that disc also has other things that you want to pass through the disc. Okay, one of them is that maybe the driller people know, drilling people know, the subsurface safety valve. You heard of it or not? Okay, yes. Okay, we usually send. Well, let's say, okay, we have, and it's usually around 100 to 200 meters, okay, below the wellhead, you have a valve, okay, which is like thread in as part of the completion, as part of the tubing, and that requires a line, a hydraulic line, that is always keeping pressurized, okay? It's always keeping pressure on that valve. So it's always keeping it open. The moment when something happens, okay, let's say an accident happens here at the top, comes a rig or a machine, something happens, and cut the communication of that hydraulic line, that valve is going to automatically close. Okay? Because it's a fail-safe mechanism. What happens if it comes a crane or happens a hurricane or something happens that knocks out the Christmas tree? The well will be producing without control. So that's why they decided to, many years ago, especially after this war in Kuwait, if you remember, there were some images of wells just burning, okay, a bunch of wells in the desert just burning. So they, by introducing this subsea safety valve is the hydraulic line has always to keep it open, always. Okay? And when that's not connected, when something happens, it's going to close. And I think I have a video. Let's see. We have one in the lab. No. Is that one? But let me check if... So let me check if I have... Okay, it looks like that. That's the top. That's the top part. Now we're going up. This is the big spring. It's going to keep it closed. And here you have these pistons that are the ones that are operated by hydraulic fluid. Okay, but the main part of the valve is this part here. Okay,
So you see you have a flapper that opens and closes, this one here.
okay, that either opens or closes. And how does it open? It has so here.
The wall is secure. 200 meters, 100 meters below the surface.
So you have to pass all of this long story is because you have to make a hole in this tubing hanger to pass the hydraulic line. Okay, and you might have other things. If you have, for example, a pressure transducer, sometimes they put a pressure transducer socket here at the bottom of the well. Okay, so they have to send another line for that also as well. Okay. Sometimes you have a pump inside the well, so you have to send to make another hole. So at the end, that might end up that hanger might have a bunch of holes. So you have to be careful that you just don't have the whole space, but you have less than that. Okay, because of all of these, they are called penetrators. Okay, that I have for putting all kind of things, and if I have more equipment, sometimes I don't want to, but there are some devices that they create, it's like a sleeve, okay? They create open and close some sections of the tubing. So for that, I also need a hydraulic line. Okay, the other two, the liquid loading and erosion, we are going to cover later this week, okay, hopefully. So now we talked pretty much about the tubing. What will happen with IPR with time? Okay, if you remember, this was PR, right? And this was 304. Let's say now it goes down to 250, for example. How will the curve look like? Okay, it's going to look something like that, right? We say it will decline. Okay, thus the intersection point, it will also produce less rate in decline. Okay, and that you can try very easily on your Excel sheet. You change here reservoir pressure, for example, let's try 270. Okay, and now the IPR got reduced, and now the intersection is not anymore at 283, but is at 240 something. Okay. So these things, they affect the intersection, depletion in our case, and tubing diameter. Now let's make one thing that I think is going to be a bit confusing, but I think that's a way to. So let's now, in our well that we have, let's move the equilibrium point. Okay, we were looking, the equilibrium point here was at the bottom. Okay, and that we use for many, for example, for design of artificial lift, we use the equilibrium point here because we normally put the gas lift valve or the ESP, electric submersible pump, down here, or and we do it at the wellhead when we want to design choke, for example. Okay, so we use. So let's now choose the equilibrium point at the wellhead and try to repeat the same analysis. Okay. So what happens if now we move the equilibrium point at the wellhead? Okay. Okay, we have our well. And here we have wellhead. Okay. And here we have our separator. Okay. And now my equilibrium point will be exactly here. How do I do that? We look first at the boundaries, remember, where the pressure is fixed, and then we move from there. We move from reservoir to PWF, co-current, then we move from PWF to wellhead, co-current, and then we stop. And that's the available pressure at the wellhead. That equation we're going to call WPR, and we're going to call it wellhead performance relationship. And now I have to do the same from the separator to the wellhead. So how is that curve going to look like? From the separator to the wellhead. We are saying in all of our analysis, right, that P separator is very close to P wellhead, okay, because they are relatively close and they are the same. Thus, that curve is not a curve really, it's just a constant number. So that's the required pressure at the wellhead, just a constant number. How is it going to look like? One curve is going to look like that, the available pressure, and the required pressure, in this case, is just a constant. So that's how it should look like. So let's try to do it in our exercise. Okay, in the same Excel sheet, here we have WPR available. So let's try to do it here. So we have already calculated the IPR part, right, which is here. Now we just have to calculate the TPR, the tubing. Which equation are we going to use? Remember, we have many, tubing Q, tubing P1, and tubing P2. Which one do we need? P2, right? We want to calculate pressure at the discharge of the tubing, at the wellhead. So I say this one will be tubing P2, and tubing P2 requires the CT, and I block it, requires the S, and I block it, requires the pressure at the bottom of the well, that I'm going to use just the pressure, the same pressure for the IPR, right? And it requires the rate. So I have to use the rate for, and this I cannot block. Okay, I want to drag down and I want to select the other cells. Okay, so here I got a issue. Did you get the same problem? Okay, I move from reservoir to bottom hole, that's the IPR equation, and then I move from the bottom hole to wellhead with the tubing equation. And that equation P2 calculates co-current, the pressure at the discharge of the tubing. Okay, so what happened here?
So what's the value of P1?
P1 is just this one. bottom hole pressure. Okay? And the flow rate, I'm using the same point there. So what happened here with this value problem? Okay, this value, if you remember, the equation was but if I want to clear PWH, this will be PWF okay. And what is happening is actually this part is greater than this part. Okay, that means that I will never ever be able to flow with that pressure and with that rate. When I try to reach the top of the well, I just get negative. Okay, I will have to create less than vacuum, okay, to be able to flow that rate. So these two is just because of that becomes negative, and then I have just a square root of a negative number. Yeah, I'm just saying why do you get the value there? Okay, so I'm saying we're calculating wellhead pressure. Okay, and wellhead pressure according to that expression is this here, and just simply this part is bigger than that part. Okay, so I have problems. Now let's go to the plot. Okay, and you should get a plot like that. So what is the difference between the blue and the red and the green? The difference, what is that difference here between these two? If I take at a given rate, the pressure, the difference between this and that. The flow in the tubing, right? That's the pressure drop due to the drawdown. Okay, just the flow in the reservoir from 304 to this number. And from here to here is the pressure drop due to the tubing, due to the presence of the tubing. Okay, but you see it has exactly the same shape. So our analysis is very powerful because of that. We have to find the shape. So let me take that figure just to put it on the notes. Okay, so for any given rate, that difference will be delta P in the tubing. Okay, and you see it becomes bigger and bigger for higher rate, which makes sense. You have like the friction losses start to get very, very important. Now let's calculate, that's the available pressure, that's the WPR. Okay, available pressure at the wellhead. Now let's make the intersection. We always have to make the intersection. We have to intersect it with simply separator pressure, right? So we have to create now one column, okay? There will be P separator. Okay, and that will be this number constant. Okay. And then I plot, I think it should be maybe plotted, not yet. So I have to add this to the plot, separator pressure. For this rate range, separator pressure is just a constant line, okay? Okay, so don't be confused. The red one intersects with the blue one. Intersection at the bottom. Okay. Now, the green one, I move the point. I move it to the wellhead. Okay? So I have the available pressure at the wellhead. And then I have the required, which is the separator pressure. So that's the new operating point. But I ask you, should it be different, the equilibrium rate? No, it should be the same. What is so powerful about flow equilibrium doesn't matter where I do it. In the middle of the tubing, inside the formation, at the top of the well, in the separator, it should give you the same number. So you see here, these two, they give you exactly the same rate. Okay, exactly the same intersection.
Professor, we didn't get to how you punch the values on the table there.
It's a constant number. It's just 40. Okay, it's just constant. It's separator pressure. And then I include it in the plot. I just include it here and use here. Okay, so that point is what I call, this point is bottom hole equilibrium. Okay, that will be IPR plus TPR, and this one will be wellhead equilibrium. And that will be WPR and P separator. Huh? Inflow performance relationship. Okay, and they should give you exactly the same equilibrium rate, which I think was 2.83 million standard cubic meter per day. Exactly the same. No matter where I make my equilibrium, it should give me the same number. Yep, that's clear? Now, I ask you if you understand that, right?
Could you repeat that explanation?
What are the red and the blue curves? What are those? For those curves, I'm setting my equilibrium point at the bottom of the well, right? So I move from the reservoir to the bottom of the well with IPR, right? And that's the blue curve, okay? And then I move from the wellhead, which has constant pressure of 40, down to the bottom hole, and that's the red curve. And I did intersection. That was very easy, clear, okay? Now I move the equilibrium point and I say I will do the same, but I'm going to put it at the wellhead. Okay, so I have to move from the reservoir to the bottom hole, from the bottom all the way to the wellhead. And that's the green curve. Okay, the green curve involves IPR and TPR, both tubing, flowing reservoir, and flowing tubing. And now I have to say against which pressure. And we know the pressure at the wellhead is constant. It's simply separator pressure. Okay, so I just put a constant line. And the intersection of these two at the wellhead, that gives me the equilibrium point, which is exactly the same as the equilibrium point made at the bottom.
That means that inside of the tube doesn't change.
Yeah, it's the same system. So if you put it together, it should always give you the same. Now, to make it one more step more complicated, just focus on wellhead recreation. Okay? Can I produce 1.5 million? What would be some ways to produce 1.5 million? Let's say I come with this number to the reservoir engineer and say I want to produce 2.8 and he gets to wipe with his face. No, you're going to produce too much sand. You're going to damage the well after a few months production. You have to produce 1.5. This formation is very, it is not very consolidated, so it's going to start producing too much sand. You're going to damage the well. You have to produce at 1.5. What do you do? Hmm? That's one option, right? We said reduce the diameter. So what effect does it have on this curve to reduce the diameter of the tube? Remember, we said the difference, the delta P in the tubing is this difference, right? So by reducing the diameter, we actually create a curve which is like that. Okay? Yes? So we'll have to reduce, that's one solution, but we have to reduce it pretty much, okay, to get exactly to 1.5. What is another solution? Remember, so let's look, that's why it's important to look at the wellhead, okay, how it looks like. Okay, we have this collection of valves, right? And then there is something we are missing here, which was very important in our drawing, the control element. That was the choke. Okay, so here you have P separator, right? And here you have P wellhead. And so far we are assuming they are the same. Okay, this pressure of the separator is the same as that pressure because there is no choke. Now, what happens if I have the choke? These two pressures, they are not the same anymore because I have the choke in between. Okay, I have that guy in between. So if I want to produce that rate, it means that I have more pressure than what I need. Okay? I have around, for 1.5, I have around 190 bar, and I really need 40. So I need something to reduce that energy drastically in one way. And the element, the perfect element to do that is the choke. Okay, so I burn all this energy and to bring it exactly. Okay, so that will be, if I want to produce 1.5, that will be the delta P of my choke. Okay, I go and I say, reservoir engineer, no problem. I will make all your dreams come true. You go to the field and you say, operator, move the choke to put a choke of 120, for example. So the solution. Now, if I want to put 1 million, for example, if I want to produce 1 million from this well, do the same, right? I have this amount of energy available, I have this amount of energy required, and then just reach it. Just closing the choke. Okay, now
this doesn't make the optimal point. It's the optimal point plus the delta P choke.
Well, here we're not, if we have an element in between, the two don't have to be the same anymore. Okay? So now we don't have any intersection. If we have no element in between, okay, we have no choke. These two have to be the same. Okay. But now if we have something in between, we don't have equilibrium anymore. We just have something that is bridging that before.
We will have different curves.
Yeah. They will have just okay. That's here. Now, one more complication. If I want to produce a ray which is here, to the right of the intersection, what can I do? Let's say that I want to produce a rate which is 2.9 e to the 6. Okay, I want to produce that rate. Without changing diameter. I want to if you see, first look at the energy. Okay, I have less pressure than what I need. Okay, I have a difference of maybe this is maybe 20 bar, I need 40 bar. Okay, so I need 40 bar difference. So I have to give energy to that fluid. How do I give energy to the fluid? With a compressor, right? The compressor gives energy and it's going to reach that. So here I would say if my reservoir engineer wants to produce 2.9 instead of 2.8, I use process and say we have to install a wellhead compressor that gives me 21 to reach that distance. Okay? And at that moment, remember, not anymore, the two pressures are not the same anymore. Okay? They are different. Huh? You put a compressor on the wellhead. Okay, so you have here, instead of having the separator, you put a compressor in between. Okay, and the compressor has to give you a delta P of 20 bar.
Like pump.
Yeah, works like a pump. Okay, so let's put here a small note. Wellhead equilibrium, choke management, or it can be used for compressor planning, while bottom hole is better for artificial lift. Okay? For example, when I have not in these wells are gas, what we're looking at. But if we have, for example, an ESP, okay, electric submersible pump, we're going to talk a bit later about that. So we have the bottom hole pressure, and then we have the pressure at the discharge. We have these two curves. Okay. That will be pressure, and that will be rate. Okay, and this will be bottom hole pressure and the pressure at the discharge. If I put no pump, the two of them are exactly the same. Okay, the two of them have to be operating here. Now, if I put the pump and I want to produce this rate, Q star, okay, then the pump has to deliver that particular delta P. And I have to go to my manufacturer and say, I need for this rate a pump that can give me this delta P. And from there you get a pump of certain size, of certain motor, certain cost, whatever. Okay. The same thing here. You go, the choke, I need a choke that gives me for 1.5, it will give me 120 bar. And they find it for you. In the storage, okay, that's the choke you need. Take it and use it. That clear? Yes? Yes. Should we take a break or do we finish a bit earlier?
You can finish a bit, then you finish.
Okay. But your brain is working fine? Or yeah? Okay. So let's take one more complexity and say now we have, because not only, as I mentioned earlier, okay, we have flow in tubing, flow in IPR, but we have also flow in the gathering system. We have the flow in the flow lines, in the pipeline. Okay, so like in this case, in this well that we were discussing, okay, in some fields, like for example, mainland US, The separator is indeed very close. It's just a few hundred meters from the well. So you can make the assumption really wellhead is basically reservoir separator pressure. But some cases you have a pipeline which is relatively long. Okay? You have a flow line. Okay? And then the flow line, the distance between the point with constant pressure is no longer the wellhead, but you have it all the way here. Okay? So you have to make your equilibrium now including flow in the flow line. Okay? Luckily for us, for gas, we can use the same tubing equation, right? Because the flow line is just nothing more than a pipe which is inclined. So the pipe can be inside the well, can be outside, can be any place, can be in space, but the same equation is going to use. For gas, we can use the tubing equation for flow in the flow line. Okay. So now let's look at many cases, unless it's a system subsea where you have a lot of changes in terrain, elevation. So for most cases, flow lines are fairly horizontal. Okay, the change in elevation doesn't really do much. So how the equation will change now, this tubing equation, if we have a horizontal line? S, if you remember S, right, now it's going to be 0. Okay, because S had L cosine of alpha, and when alpha is exactly 90 degrees, the cosine is 0. Okay, so that's fine, that's perfect. Now what happens with CT? If you remember, let's see what's the definition of CT. Okay, CT was this guy here. So here we have a problem. Okay, what is the problem on this CT? Here we have e to the 0, that gives you 1, minus 1, 0, divided by 0. That's a problem, right? How do we solve that issue? You remember another French guy, French, they made a lot of advances on but you have that when you have a problem, right, you have that the limit of an expression of a function x is undefined when x tends to 0, is undefined, right? What do you do? We have to call again Kalashnikov, okay, once more to help. Okay, so what do we do in that case if it's undefined? Yeah, at the top and at the bottom, you remember that guy called L'Hopital? Yes? To the angle? Yeah? The angle is between, if you have the pipe like that, is this angle or this angle. So if it's horizontal pipe, this will be 90. Okay? So L'Hopital tells me that I take the limit of the derivative of both, right? And then I check again if I have a problem with this, which is undefined. The expression I have in my case is s at e to the s minus 1. And when you apply the derivative on that, that will just give you e to the s and 1 here. And that gives you simply just 1. Okay? So at the end, we end up with the expression called QGC is not anymore tubing, but is flow line times P. Okay, let's call it P in squared minus P out squared to 0.5. Okay, so that's the expression for horizontal pipeline. Okay, you can do the math. You can have it as homework if you're bored. You can go and derive it. But you have to say, you trust me, that's the expression. I get rid of the S, and I had this issue with S over E to the S, so I applied L'Hopital, Kalashnikov will be happy, and then we got this expression, okay, for horizontal pipe. P in minus P out to the 0.5. So now, let's go back to my exercise that I have, and let's now include a flow line. Okay, now let's say the separator is not very close, but it's far away, and I have a flow line in between. Okay, and I'm going to make wellhead equilibrium. So let's just be clear. Let's put again our system before you start doing calculations. Okay. Okay, now we have a long pipeline and a separator, and I'm going to choose the equilibrium point again here. Let's say no choke. Okay, we're not including choke here. No choke. Again, I go from here to here and here to here, right? TPR and IPR, and I find WPR, right? That curve we have was the green curve that we calculated before. Okay. Now, from the separator, I have to move counter current all the way to the wellhead. Okay, that means I have to use that equation. How do I use the equation? I have the Q, I have the P out, and then I calculate P in. Okay, that means the required pressure at the inlet of the flow line to flow against 40 bar. Okay, how is that equation going to look like? If I make now wellhead, P wellhead, we know one looks like that, right? That's the WPR, and the other just going to go up, okay? Just like that. And how do we call that curve? We have to give it a name, okay? Everything else has a name, so it's going to feel sad if we don't give it a name. FPR, okay? Flow line performance relationship. Okay, so let's do that last step, and then we can go home and just get some rest for the brain. Okay, so I call it here FPR, flow line performance relationship. P wellhead required in that case. Okay, that will be in bar also. And let's see the equation with alt F11, how the equation is called. And the equation is basically line, okay? Because it can be a flow line, can be a pipeline, so I just called it line. And you have two equations, P1, P2. Which equation should I use? P2, that's going to give me the pressure at the discharge of the flow line. Is that what I want? I want the pressure, if we look at my drawing once more, we have this pressure, that's the pressure at P2, and we want P1. Okay? So we have to use is P1. Yeah, we want to calculate, here we came from the reservoir all the way to the wellhead. Okay, we came counter current. That's clear. Okay, so now we have to go from the other point where the pressure is fixed to the wellhead. Okay, so we have to move here counter current. Remember, the flow goes on this direction. Okay, counter current to calculate that pressure. The required pressure I need at the inlet of the flow line to flow against that pressure. Okay, so according to our equation, this is P1, this is P2, and I have the rate. So I have the pressure I have the rate, and then I want to calculate P1. Okay, so that means I want to calculate P in from this equation. Okay, so let's say here I call it line P1, okay, and I insert the flow line coefficient. I calculate it the same way as for tubing. P2 will be separator pressure, and I block it, and Q will be, well, the same Q, right, that I have been using before. Okay, so then I plot it. Okay, I'm using DCT CF, sorry, I'm using this pressure, which is fixed, and then I'm using the same range of rate that I use for the IPR and for all the rest. Okay, and I obtain something like that, flow line performance relationship, which is very close to separator, right? It means that that pipeline should be huge. It should have a very big diameter. But you see, the intersection point doesn't change really that much. Before it was 2.83, and now I made 2.75. So it doesn't change really that much, the intersection. But if you want to see the effect of a smaller pipeline, you can just change the flow line. We use now this one for. Okay, and now it has a bigger effect. Now you see that if the intersection moves from close to this base